This is a SUVAT Equations question taken from the 2018 AS Applied paper. It is the second of the SUVAT Equations questions on this paper. I think the question just before this one, question 6, was also a SUVAT Equations question. So we've got a train travelling along a straight horizontal track between two stations A and B, so a motion in a straight line. In a model of the motion, the train starts from rest at A and moves with constant acceleration 0.3 meters per second squared for 80 seconds. The train then moves at constant velocity before it moves with a constant deceleration of 0.5 meters per second squared, coming to rest at B. So there's three parts to this question. First part also has three parts within it. For this model of the motion of the train between A and B, state the value of the constant velocity of the train, state the time for which the train is decelerating, sketch a velocity time graph. And then it goes on to give you the total distance between the stations, and then find the time taken to travel between A and B, and then a very typical suggestion of improvement in part C. So there are 7 marks available altogether. So we'll start at the beginning. Now what I'm going to do is first of all write down the SUVAT equations, because I've seen here I've got constant acceleration, then I've got constant velocity, which is also constant acceleration, just acceleration of 0, and then constant deceleration, which is constant acceleration across the board. So we can use the SUVAT equations whenever we have constant acceleration. So my SUVAT equations are, we'll start with the S ones. S is u plus v over 2 times t, where S is displacement, u is initial velocity, v is final velocity, t is time. And then we've got other equations where instead of v in this one, we've got a, acceleration, and instead of u, we've got v in this one. That last one there is not as recognised, but easy to remember since it's similar to the one above. So you might as well write them all down. And then you've got the v equations, which are v equals u plus at, and v squared equals u squared plus 2as. Okay, so I'm going to decide which one of these equations I'll use in a minute, depending on the information. But we will need to process the information to start off. So we were told we had 2 stations. So here's station A. I'm going to give it a hat because it's not acceleration. And then station B, and you've got the train travelling between A and B. And we can kind of split it into sort of like 3 sections, I guess. So there's different types of motion going on in between these points. So a bit of a rough sketch as to where they are, but I'm going to put down my information in between nonetheless. So in the first section, so in the model of the motion, the train starts from rest at A and moves with constant acceleration 0.3 meters per second squared for 80 seconds. So let's put that on here. I've got A being 0.3 meters per second, and I've got time being 80 seconds. And I was also told that the initial velocity is 0 because it starts at rest. That's my u. Better make sure that looks like a u and not a v. Well, that's even worse. So u. Okay. So in the second section, the train moves with constant velocity. So that's the only part, a bit of information we're told for that one. So we know that A is 0 for that bit. And that constant velocity is going to be the same as the V in this first section. And what about the last section? It says the train then moves at constant velocity before it moves with constant deceleration of 0.5 meters per second squared, coming to rest at B. So my acceleration on this last part is negative because it's deceleration. and I'm told that the final velocity is 0. So that basically sums up the information that we're given in a nice little diagram. And for the first 3 marks in this question, we are asked to state the value of the constant velocity of the train. So that's this middle part here. That state the time for which the train is decelerating. So over here. And then sketch a velocity time graph. So that's going to be a very basic sketch, given it's worth probably just the 1 mark. So part A. Question 1. So this was state the value of the constant velocity of the train. So I want to find my V, in this section, because it will be the same for the next section. So I need an equation that relates AT, U and V, and it should be this one. So final velocity is initial velocity plus acceleration times time. And I know that my initial velocity is 0, with my acceleration being 0.3 and my time being 80, given that as 24 meters per second. So my train accelerates in this section 0.3 meters per second squared from rest, and by the time it gets to the end of this section it is travelling at a speed of 24 meters per second, and that's for 1 mark. The second part, state the time for which the train is decelerating. Whoops. So we're in this section. So I enter this section at the same velocity as what I entered the last section. So there's a constant velocity in this one. So my initial velocity in here I can now write down as 24. That should have meters per second there. So I'm trying to find t in this part. So that's the same equation. The one we used just now, v equals u plus at. However, I'm finding t this time. So I've got v equals u plus at. My final velocity is v. My initial velocity is 24. And I am subtracting 0.5 times t. So rearranging will give you the solution to t as 48 seconds. And so we are then asked to sketch. So we don't need too much information here, but velocity versus time. So if I put time along here, I've got this section where I'm accelerating. So my v is increasing. I'll just call it that velocity, I should think, rather than getting confused with final and initial velocities. Then for some period of time from there, so that took us to about 80 seconds. So that should be in seconds and that should be in meters per second. Then it's constant velocity at that 24, if you remember. And then for some period of time, and then we were decelerating for a period of 48 seconds. So let's label it like this. Rather, it's only 1 mark, so we don't really need to have too much detail. So these are lengths here. So 80, I'm calling this length t, and then this length is 48. Okay. But I think a very basic, trapezium-looking diagram will suffice for this question. It's only worth 1 mark. Okay, in part B, the total distance between the 2 stations is 4,800 metres. Okay, so for 3 marks, we have to use the model to find the total time taken by the train to travel from A to B. Okay, so we're going to use this trapezium-looking diagram for this part, because we know that for a velocity time graph, the total distance travelled is the area beneath this graph. So if I can find the area of this trapezium and set it equal to 4,800, then I should be able to find that missing time and therefore the total time taken. So let's just remind ourselves, and I'll change the colour so we don't get confused. If I have a trapezium that looks a bit like this, then that's A, that's B, and that's H. Then the area of this trapezium will be half the sum of the parallel sides times the distance between them. Okay, so in my case, for this diagram, the total area, which I know to be 4,800, will be half of the sum of the parallel sides, which I've got this t up here. I need to add on the bottom, which is t plus 80 plus 48, so plus another t and 128, and multiplied by the distance between them, which is 24. And tidying that up gives me 2t plus 128. And so, solving this for t, so let's expand this. So 24t plus 1,536. Subtracting that from both sides and dividing both sides by 24 gives me t equals 136, but that was just this section here. And so I have to add on 128 to find the total time. So 136 plus 128, making the total time that the train is travelling 264 seconds. So for the final mark for this question, we are asked to suggest one improvement that could be made to the model of the motion of the train from A to B in order to make the model more realistic. Okay, so we very basically gave a model for this train's motion where you had constant acceleration, then constant speed, and then constant deceleration. However, that's quite unrealistic. That's not how trains tend to move. What you would expect more typically from a train is to have variable acceleration, in which case you would not be able to use the SUVAT equations. So you wouldn't you carry on using the SUVAT equations and assume constant acceleration in these questions. But other questions, of course, may ask you to use calculus when you have variable acceleration. That concludes the question. And if you want to see more SUVAT videos or some more explanations, go to the SUVAT page at studyworld.com.